Curvilinear coordinate systems 15. A particle is moving in three-dimensional space. Describe its position r of t, velocity r dot, and acceleration r double dot in terms of the spherical coordinates and basis vectors. To work this problem, it will be necessary to take time derivatives of the basis vectors because they will change as the particle moves in space. So we can start by determining the basis vectors in the spherical coordinate system. For that, we need the position vector r in Cartesian coordinate system, which is x ex hat plus y ey hat plus z ez hat. And we know the conversion between spherical and Cartesian coordinates. X is equal to r sine theta cosine phi So theta is our polar angle, phi is our azimuthal angle. This is in ex hat direction. And then we have the y component, r sine theta. This time we have sine phi, projection onto the y-axis, ey hat direction. And then we have the z component is r cosine theta in ez hat direction. So this is our position vector. Next, we need to take a derivative of this with respect to r. So del r position vector with respect to the r radius of the sphere. This will give us, because we have only r's as a pre-multiplier for each term, so this will just get rid of the r's in each term, and it will give us sine theta cosine phi in ex hat direction plus sine theta sine phi in ey hat direction, and then we have cosine theta in ez hat direction. Now, in order to find the scale factor h sub r, I need to look at the magnitude of this vector del r derivative of position vector with respect to r. And now you can see that I will have x component squared, y component squared plus z component squared inside the square root. So I will have sine squared theta parentheses cosine square phi plus sine square phi. And then I will have cosine square theta, and this is all inside the square root. And sine square plus cosine square is equal to 1. So I obtain again sine square plus cosine square, which is again 1. Therefore, I find that the scale factor h sub r is equal to 1. So that's the conclusion. And with that, I can write the unit vector er hat. And this unit vector er hat is 1 over the scale factor h sub r del position vector del r. So since I'm just dividing it by 1, I can write my ER hat unit vector, and it's exactly equal to this because I'm just dividing it by 1. Okay, so that was the unit vector ER hat. Now we can work on the theta part. So let's take a derivative of the position vector r with respect to the angle, polar angle theta. So from r sine theta cosine phi, I will get r cosine theta for the x term, r cosine theta cosine phi in ex hat direction. Y term was r sine theta sine phi, and that derivative will also give me an r cosine theta. So r cosine theta sine phi in EY hat direction. The last term was r cosine theta. That derivative will give me minus r sine theta in EZ hat direction. And now I can take the magnitude of this vector, which will give me the scale factor h sub theta. That's magnitude of the derivative of position vector with respect to the polar angle theta. Now you can see that I have in r parentheses cosine square theta, cosine square phi, cosine square theta, sine square phi, and sine square theta. So this will give me r times cosine square theta. Then in the parentheses I have cosine square phi plus sine square phi. So I'm taking the x component square, y component square, and z component square, sine square theta, and this is all inside the square root. And once again, cosine square plus sine square is equal to 1, and I have the same thing going on here. Therefore, at the end, I obtain the scale factor h sub theta is equal to r. So I'm ready to write the unit vector e theta hat. It is 1 over the scale factor h theta del r del theta. So all I have to do is take del r del theta here and divide it by r. So I'm going to have this divided by r. So let's get rid of the r's. Then my answer is cosine theta cosine phi ex hat plus cosine theta sine phi ey hat and minus sine theta ez hat. Now I'm ready to work on the phi part. So let's take a derivative of the position vector r with respect to the azimuthal angle phi. So the first term was, remember, r sine theta cosine phi. The derivative of the cosine will give us a minus sign. So we will have minus r sine theta sine phi in ex hat direction. And then we had for y r sine theta sine phi, that will turn into a cosine phi. So we will have plus r sine theta cosine phi in EY hat direction. And for the z part, there is no phi dependence, so plus 0. Then we can write the scale factor h sub phi. This is the magnitude of this. You can see that r sine theta is common, so r sine theta square root sine square phi plus cosine square phi is what we will have. So r sine theta parentheses sine square phi plus cosine square phi this is inside the square root, and this is also equal to 1, so we obtain our scale factor h sub phi is equal to r sine theta. Now we're ready to write the unit vector E phi hat. E phi hat is equal to this derivative del r del phi divided by the scale factor. So we're just going to copy this derivative and divide it by the scale factor. So divided by r sine theta divided by r sine theta. So the answer is sine phi, but there was a minus sign here, so minus sine phi ex hat and plus cosine phi ey hat. This is our unit vector. Now we can summarize these results, so let's do a summary of these results. We have found the radial unit vector er hat to be sine theta cosine phi in ex hat direction and sine theta sine phi in ey hat direction, and then we have cosine theta in ez hat direction. This was our radial unit vector. Now the azimuthal unit vector e theta, the polar unit vector e theta hat, that was cosine theta cosine phi in ex hat direction and cosine theta sine phi in ey hat direction. And finally we have minus sine theta in ez hat direction. And the last unit vector, the azimuthal unit vector E phi hat, was found to be minus sine phi in Ex hat direction and plus cosine phi in Ey hat direction. So in order to continue this calculation, it's mentioned in the problem statement that we will need the time derivatives of these basis vectors. So now that we have obtained all the scale factors and the corresponding basis vectors, we can start working on the time derivatives in our next video.